Section 3.3, Derivatives of Trigonometric Functions. We're going to start by just looking at the sine function to begin. And we're going to draw that function, just one period of it. And then we're going to apply something that we did in previous examples of looking at a graph and trying to think of where do we have that the graph is increasing or decreasing, or how that translates to where is the slope positive, where is the slope negative, and then also where is the slope 0. So the sine function we should all be familiar with. I'm just going to look at from 0 to 2 pi. The amplitude for f of x equals sine x is just 1. So my graph is going to go up as high as 1 and down as far as -1. At the beginning of the period, it's at 0, equilibrium. And then it goes up when sine of x, when x is pi over 2. We get that sine of x is 1. And then we then go back down. When x is pi, sine of x is 0. And then at 3 pi over 2, sine x is equal to -1. And then we just return back to equilibrium at the end of the period length at 2 pi. And we just get our familiar sine wave shape. So we can definitely see, even as I was drawing that, we have places where the graph is increasing. But then it changes to decreasing. And when it does that change, that's where we get a 0 slope. So we have that the slope is equal to 0. That was one of the questions that I brought up a minute ago. The slope is equal to 0 when x is equal to pi over 2. And we also have another value where that happens. The slope is equal to 0 at 3 pi over 2. And then between those places, we have positive or negative slopes. So from 0 to pi over 2, we have a positive slope. And then from pi over 2 all the way down to 3 pi over 2, we have a negative slope because it's decreasing. And you can think that it starts at a small negative value, something close to 0, then increases to a highest negative value, and then goes back down closer to 0 again, because then it transitions in the interval 3 pi over 2 to 2 pi to a positive slope again. So the derivative of sine of x, this is what we're focusing on by looking at these slope values. The derivative has these qualities. It is positive between 0 and pi over 2, and also positive between 3 pi over 2 and 2 pi. But it's negative between pi over 2 and 3 pi over 2. And then we also have that the derivative is equal to 0 when x is equal to pi over 2 and also 3 pi over 2. When we think of just that concept, mixing it in with trigonometric function values, the patterns we see seem to indicate that f prime of x is equal to cosine of x. Because if I was to draw what we just described, we have values at pi over 2 and 3 pi over 2 where the function is 0. Between pi over 2 and 3 pi over 2, it's negative. And then between 0 and pi over 2, it's positive. And between 3 pi over 2 and 2 pi, it's positive. So we're just noticing a little bit of some patterns. That's all. Let's see if we can prove that to be true. So we're going to do this by starting with the definition of the derivative. So we were told that f of x equals sine x. That's what we named it before. So we're going to be looking for f prime of x which is just, by definition, the limit as h approaches 0 of f of x plus h minus f of x divided by h. Our function is the sine function, so we have sine of x plus h minus sine of x divided by h. And then we're going to use the sum formula for sine, meaning sine of a plus b. That was a formula from trigonometry. So sine of x plus h becomes sine x cosine h plus cosine x sine h, and then we still have minus sine x, all divided by h. And we're going to split this up into two fractions that are being added. The limit as h approaches 0, and we're going to keep together the things that have sine x. So I'll have sine x cosine h minus sine x, all divided by h. And then the other fraction will be the one that has cosine x. What I'll do next is split off the functions that have x. So in my first fraction, you can see that we have a common factor of sine x there. So I'm going to write this as sine x times the fraction cosine h minus 1 divided by h. This should remind you a little bit of what we saw with the exponential functions. And then on the next fraction, I'll take out the cosine x by just factoring it out. And I have this other fraction, sine h over h. And then I'm just going to use a limit law. Essentially just distributing the limit throughout the product and the sum. So I'm going to have the limit as h approaches 0 of sine x times the limit as h approaches 0 of cosine h minus 1 divided by h, plus the limit as h approaches 0 of cosine x times the limit as h approaches 0 of sine h over h. And I'm allowed to do this if those limits exist. So again, we haven't really proven anything yet. We're just following this to see if we do get limits that exist, and then maybe that leads us to a conclusion. When we get to the end of what I've just written, we now have 4 limits to evaluate. The limit of sine x as h approaches 0 or cosine x as h approaches 0 is just those respective functions because they don't depend on h. They're constant relative to that. So in fact, what I really get is sine x times the limit as h approaches 0 of cosine h minus 1 over h plus cosine x times the limit as h approaches 0 of sine h over h. So now I just have 2 limits left to evaluate. You can go back to section 2.2 and you can see that the limit as h approaches 0 of sine theta, that should say h there, divided by h, that's equal to 1. We had used theta back in section 2.2. And you don't need this part. Forgot to delete that. So back in section 2.2, we can find out that this limit here, that's just equal to 1. So notice what we have. I have cosine x times 1 at the end of this, and then I have sine x times this one remaining limit. And if we want to prove that the derivative of sine x is equal to cosine x, we are going to hope that this limit as h approaches 0 of cosine h minus 1 divided by h, we're going to hope that that's going to be 0. So we're going to do something with this that is similar to what we saw with limits of fractions that involved rationalization. So I'm just going to write down limit as h approaches 0 of cosine h minus 1 divided by h. And I'm going to use a multiplication of a conjugate. In this case, cosine h minus 1, or sorry, plus 1 divided by cosine h plus 1. We saw something like that work before with square roots, and trig functions work sort of in the same way, mainly because of the Pythagorean identity. So in the numerator, I have cosine h times itself, so cosine squared h, then plus cosine h, then minus cosine h, and then minus 1, all divided by h times cosine h plus 1. I can combine like terms in the numerator. Limit as h approaches 0 of cosine squared h minus 1 divided by h times cosine h plus 1. And then I have a Pythagorean identity in the numerator. Cosine squared h minus 1 is the same thing as negative sine squared h and then what I'm going to do next is have a product of fractions, where in the numerator I have two factors of sine h, so I'm going to have negative sine h divided by h, and then times the other fraction will be sine h divided by cosine h plus 1. And again, we're allowed to do that by limit laws if essentially when I take the limit of both pieces of this product, the limits exist. So in fact, the limit as h approaches 0 of the first factor of that product, negative sine h over h, that does exist because we just talked about it up there. And then the other limit, it also will exist because we can use continuity to essentially plug in 0 for h. And what we get is that the first limit is equal to negative 1. It's just the negative of the limit we established before, the one that came from section 2.2. And then the second limit is sine of 0 divided by cosine of 0 plus 1. That just becomes 0 divided by 1 plus 1, or 2. Both of those limits, both of those give us values that when divided tell us that the limit exists, and so therefore the whole product just becomes 0. So what we just found out is that the remaining limit that we needed to figure out, that's equal to 0. So then my whole definition of the derivative comes down to sine x times 0 plus cosine x times 1, which means that the derivative of sine x is cosine x. Just putting together the limits that we figured out. And that's it. The derivative with respect to x of sine x is cosine x. And this is what we want to remember. You won't have to replicate the proof that I just did. It's also in your textbook. You can see it there. But this is now something that we have proven to be true, and now we just need to memorize it. In a similar fashion, we can prove that the derivative with respect to x of the cosine function is negative sine x. So now we have the derivative of sine x is equal to cosine x. We can prove in the same way that the derivative of cosine x is negative sine x. To figure out what happens for tangent x, let's use the quotient rule. The derivative with respect to x of tangent x is just the same thing as the derivative with respect to x of sine x over cosine x. Let's call sine x f and cosine x g, and we'll use the quotient rule, which is f prime g minus g prime f, all divided by g squared. And what that will give us is the derivative of sine x, which we just said is cosine x. So notice that's f prime, as in I called f sine x. And then I multiply that by g, the bottom of the fraction, which is cosine x. So that's g. And then minus g prime, which is the derivative of cosine x, which we just said was negative sine x. So that's g prime right there. And then times f, which again was sine x. And then we divide all of that by g squared, which is cosine squared x. So simplifying, cosine x times cosine x is cosine squared x. Then I have minus a negative sine x times sine x. That turns into plus sine squared x. Divide all of that by cosine squared x. The numerator is the Pythagorean identity, which gives us cosine squared x plus sine squared x is equal to 1. And then we can use the reciprocal identity and state that this just gives us secant squared x. And what this has told us is that the derivative with respect to x of tangent x is equal to secant squared x. So now I have those first three organized here. This comes from your book as well. And you can use similar methods like the quotient rule to figure out the remaining three, since cosecant x, secant x, and cotangent x are all reciprocals of the ones we just talked about. We can just use the quotient rule and we get these remaining three. And I'll point out a couple of patterns with this. There are 6 derivatives that we have here because we have 6 different trig functions. 3 of them are positive and 3 of them are negative. The ones that are negative are the derivatives of cosine, cosecant, and cotangent. And when you think of those words, cosine, cosecant, cotangent, they all start with the prefix co, because these are all related to the idea of cofunctions and complementary angles. So you can just remember that the derivatives of the cofunctions, those will be the negative derivatives. The derivative of cotangent x is negative cosecant x. The derivative of secant x, which is in the middle here, that gives us secant x tangent x. And then the derivative of cosecant x follows a similar pattern. It's just that it's negative. So the derivative of cosecant x is negative cosecant x times cotangent x. So this box here, which you can also find in the textbook at the bottom of page 193, that becomes something now that we want to memorize. So you want to memorize these derivatives for these functions. So now let's just put them all to work. One thing to keep in mind as we move forward into later chapters, we do want to remember that for the most part, we are measuring the angles for these trig functions in radians. So keep that in mind. You want to have your calculator set to radian mode too, in case you are evaluating at any point. So first, let's look at number 12 on page 196, and we're just going to differentiate y equal to cosine x divided by 1 minus sine x. And we're just going to use the quotient rule. So the numerator is f and the denominator is g. So again, we want f prime g minus g prime f divided by g squared. So in this case, f prime is the derivative of cosine x. That's negative sine x. G is 1 minus sine x. G prime will be the derivative of 1, which is 0, minus the derivative of sine x, which is cosine x. And then we multiply that by f, which is the numerator, cosine x. And we divide all of this by the denominator, 1 minus sine x, quantity squared. And then we'll just do some simplification of the numerator. Like we've seen with the quotient rule before, don't multiply out the denominator just yet. Maybe that might become important later, but for now, let's leave it factored. But my numerator becomes negative sine x, and then negative sine x times negative sine x gives me plus sine squared x, and then minus what will be negative cosine x times cosine x, so that just gives me plus cosine squared x. And then what I have in the numerator is negative sine x plus what essentially is 1 by the Pythagorean identity, because again, sine squared x plus cosine squared x, that's equal to 1. So I'm just going to rewrite the numerator as 1 minus sine x, which has the exact same form as the factors in the denominator. So in fact, it was good that I didn't multiply out the denominator, because I can cancel out one factor of 1 minus sine x. And that leaves me with 1 in the numerator and 1 minus sine x in the denominator. All right, let's look at another application of these derivatives of trig functions. This is something that may remind you of something you saw in trigonometry, essentially harmonic motion. This is example 3 from page 194. An object at the end of a vertical spring is stretched 4 centimeters beyond its rest position and released at time equal to 0. There is a figure that you can see in your book, but just as a little guide here, you can think that there's an equilibrium where if you weren't pulling on the weight, it would just be hanging there and not moving at all. But what we've done is we've stretched a string, or a spring in fact, and now the weight is 4 centimeters beyond its rest position. So you can think of this axis as 0, and then here we've got 4 centimeters. So we've stretched that. Now, if we think about what would happen if we release this, the weight would go up. And if no other friction was acting on this, like air resistance or gravity or anything else like that, it would just keep moving up and down. So therefore, its position at time t can be modeled by a cosine function. And in fact, here it is. S standing for position. It's a function of t, and that function is 4 cosine t. That gives us the position of the weight at any time t. What we want to do is find the velocity and the acceleration at time t and use them to analyze the motion of the object. So similar to a different example we saw before of finding velocity and acceleration, but this time we are just basing this off of a trigonometric function. So remember, the first derivative of the position function is velocity, and the second derivative of the position function is acceleration. And that also means that the first derivative of velocity is acceleration. So velocity, v of t, is the derivative with respect to t of my position function, s of t, which means the derivative with respect to t of 4 cosine t, which will just be 4 times the derivative of the cosine function, which is negative sine t And so that gives us negative 4 sine t for the velocity function. And now that we know that, we can take the derivative again to find the acceleration function. So the acceleration function, a of t, is the derivative with respect to t of the velocity function, which means the derivative with respect to t of negative 4 sine t, which gives us negative 4 times the derivative of sine t, which is cosine t. And what that gives us is just negative 4 cosine t, and that becomes our acceleration function. So you can see that all of these derivatives give you some very similar things. So we've essentially just got sine and cosine functions here for our position, velocity, and acceleration. And if we were to graph these, we could then analyze the results. So let's do that. These are all going to be very simple graphs. And I'm just going to look at over one period length. And we're going to use that marker as positive 4 and this one as negative 4. And the period length for all of the functions that we have here, cosine t and sine t, that's all just 2 pi. So I'm going to do this just like we saw at the beginning of this lesson. Look at what happens at pi over 2, pi, 3 pi over 2, and 2 pi. So first we'll start with the position function, which was 4 cosine t. That one starts at the top of the amplitude at the beginning of the period. And then it moves down to cross through the x-axis, or the t-axis in this case. And then it reaches the bottom of its graph at pi, halfway through the period, and then back through 0, and then again ends at 4 when time is equal to 2 pi. So this is our original function, s of t. So then again, think about what we had noticed before. If we want to find the derivative, it means from 0 to pi, the derivative is always negative because my position function is decreasing that whole time. And then at pi, it's equal to 0. So if we think about the graph of negative 4 sine t, if we were to start graphing that, at the beginning of its period, it's at negative 4 times sine of 0, which is just 0. But then it goes down. And it reaches its lowest point at pi over 2, and then goes back, and notice it crosses through 0 at pi. And then it reaches its highest point at 3 pi over 2, and then it's back to 0 at 2 pi. This is really just the vertical reflection of 4 sine of t. So this gives us our velocity. So notice we've got negative values from 0 to pi. That relates to how the position function was decreasing from 0 to pi. And then from pi to 2 pi, the position function is increasing, and that's why we notice positive values for the velocity function there. So then finally, the acceleration function, we expect some similar things to what we saw with the position function because it's a cosine function. But since it's negative, then we expect essentially a vertical reflection again. And again, this relates to how the acceleration is the derivative of velocity. Notice that the velocity function is decreasing from 0 to pi over 2. So we expect negative values for acceleration there, which is true. That's what we exactly get. But then it crosses through 0, because that relates to when the velocity function had a 0 slope. So just a simple example like this gives you a good way to, again, understand these derivatives and how they relate to the functions that they came from. So this gives us our acceleration function. Also, something else to point out, notice that if we just kept taking higher derivatives of sine or cosine, we just end up going back and forth between the sine and cosine functions. So continuing on, let's look at another example, number 4 from page 196. And here we're just going to look at a couple of other functions. Differentiate y equal 2 secant x minus cosecant x. So this means y prime, and we're going to differentiate with respect to x 2 secant x minus cosecant x. First, I'll use a derivative rule, a couple of them. I'll have 2 times the derivative with respect to x of secant x, and then minus the derivative with respect to x of cosecant x. And then those derivatives were mentioned earlier. The derivative of secant x is secant x times tangent x, and then the derivative of cosecant x is negative cosecant x times cotangent x. So this becomes 2 times secant x tangent x minus negative cosecant x cotangent x, which gives us 2 secant x tangent x plus cosecant x cotangent x. And there may be some stuff that we can do with this if we try to simplify. Here's just some good practice of using identities. If we write everything in terms of sines and cosines, maybe we can simplify this, which is something that we do want to think of, because what if I needed to take a higher derivative? Then I might have a product rule I'd have to use a couple of times. Might be a bit much. So let's see if we can simplify this a little bit. Secant x is 1 over cosine x. Tangent x is sine x over cosine x. And then cosecant x is 1 over sine x, and cotangent x is cosine x over sine x. Now I noticed then I'd have different denominators, and if I wanted to have common denominators, then I would start getting some higher powers of sine x in the numerator and higher powers of cosine x in the numerator. That might be just a bit much. So I don't think we need to simplify this. This is simple enough. So just something to keep in mind when you're working on these derivatives is seeing if you have anything that's overly complicated and if you need to simplify it. And again, where I got those derivatives from, that was just from earlier in the notes where we had all of the trig function derivatives organized in one place. So definitely make it a goal to memorize these, because you're going to need them in Calc 2, Calc 3, Math 84, and it just becomes something else to memorize with trigonometric functions.